All right, topic of today is the derivatives of non-natural exponentials and non-natural logarithmic functions. So in the past two videos, we talked about the derivatives of the natural logarithm and the natural exponential e to the x and natural log x. But of course, we work with exponentials and logarithms that are not always base e. Remember, natural log is base e. Natural exponentials base e, but we deal with them that are not natural, so we need to know how to differentiate those. So first up, the derivative of b to the x. So remember, the base of an exponential is going to be a positive number not equal to 1. So maybe 5 or 2 or 10 or whatever, okay? Or 1/2 or a third or pi. Again, it doesn't have to be an integer, just a positive number not equal to 1. So what's the derivative? Well, the derivative is b to the x. So it's the original function, kind of like the natural exponential derivative. You get the original function back, but it's scaled by the natural log of b. So the natural log of the base. So just don't forget to multiply by the natural log of the base. Okay? Now what about the derivative of the non-base base e logarithm? So again, base, same thing here. That base can be any positive number not equal to 1. So pi, 3, 6, 1/2, whatever. So notice that the derivative is kind of like the derivative of the natural version, 1/x. But we have another factor on the denominator, natural log of the base. So kind of like there's an analogous thing going on in both cases. With the derivative of the natural non-natural exponential, we have to scale by the natural log of the base, and with the derivative of the non-natural logarithm, we have to divide by the natural log of the base. Okay, so in both cases, we are doing something with the natural log of the base. Now, what about the proofs? Where do these come from? Well, you could use the limit definition, but it actually turns out you don't have to use the limit definition here, because we can use properties we've talked about recently. In fact, we can rely on. Actually, I'm gonna save the proof of the non-natural exponential. I'm gonna save that for the future, because the technique I want to use, we're not going to cover until section 2.10. But I like to use that technique because it's really simple. So I'm going to save that proof until section 2.10. I'll go ahead and prove the logarithm derivative, though. And the thing is, we can use this. We can basically prove that by just remembering to use our change of base formula. Because remember, a logarithm to any base, so log base b of x, we can always change that to a natural logarithm. And then we can differentiate using what we know about a natural logarithm. So how do you do the change of base? Well, you take the log, let's say, of your new base of your argument and divide by the logarithm new base of your old base. Okay, that's the change of base formula. But if you want to talk specifically about changing to a natural log, we could say that log base b of x is equal to natural log x over natural log, not c, b, over natural log b. So that is where that comes from. That's just the logarithm change of base formula. That comes in handy. So if you need to review that, by all means, please do so. Okay? So we change the base to our natural logarithm instead of the base b, whatever b was. But here's the thing. Natural log of b is just a constant. So there's no need for a quotient rule here, because remember, we can rewrite anytime the denominator is a constant, we can rewrite that as multiplying by 1 over b instead of multiplying by 1 over natural log b instead of dividing by natural log b, because natural log b is a constant. I know that a lot of students see logarithm and just get all confused. but a logarithm of b, which is b is a constant, the logarithm of a constant is itself just a constant. So we can factor it out, and now we can take the derivative of natural log x, which we just talked about in the previous video. The derivative of natural log x is 1 over x. So we just get 1 over natural log b times 1 over x, and then you multiply those together, and you get it precisely what we set up here in theorem 2.53. Okay, so we didn't need any heavy lifting there. We just relied on the known fact that we had already proven that the derivative of natural log x is 1 over x. So we used that fact, leveraged it along with the change of base formula to get the derivative of a non-natural logarithm. Okay? All right, again, to prove this first part, we're going to wait till section 2.10 to do that. And there's a really cool, nifty way to do that with a technique we just haven't gotten to yet. Okay? All right, so let's do a couple examples with these. See what we can come up with. All right, so we have 4 examples here. Let's see. So first one looks like a product, some trig and some non-base e exponentials. So I see a product, I immediately think product rule. So f prime is what? Okay, derivative of the first function. First function is 5dx times the second function, cotangent, plus the derivative of the second function, cotangent, times the first function, 5dx. So that is the application of the product rule. All right, and now what we're going to do is take those individual derivatives. What's the derivative of 5dx? Well, that's what we just talked about at the top of the page. The derivative is itself, 5dx, times natural log of 5. Of course, times the cotangent that was already there, plus, all right, do you remember the derivative of cotangent? Maybe, maybe not. You better memorize it soon. It's what? Derivative of cotangent is negative cosecant squared. Okay? Times the 5x that was already there. Okay? Anything that we can do to clean that up? I mean, not really. I mean, I guess we could factor a 5 to the x out. Sure, let's do that. They both have a 5 to the x in common. So that's going to leave us with what? Natural log of 5. Natural log of 5 times cotangent. Plus a minus is a minus. So minus cosecant squared x. There we go. That's about as good as we need to get. That's about as far as we need to take it. There's no reason to go any further than that. Okay? All right, what about b? Okay, b looks like we have a quotient. We have the quotient of 2 exponential functions. So let's see what we can come up with. G prime of x. Okay, quotient rule time. Get your big vernaculum. Oh, the derivative of the top function. Derivative of 2 to the x minus 1 times the bottom function 2 to the x plus 1 minus the derivative of the bottom function 2 to the x plus 1 times the top function 2 to the x minus 1. All over the denominator squared. So 2 to the x plus 1 quantity squared. I get the feeling this is going to be an ugly answer. I don't know for sure. I don't think there's going to be a lot that's going to simplify nicely, though. Okay, let's see what we can do here. All right, what's the derivative of 2 to the x minus 1? Okay, you have the sum of 2 functions, but we can take, according to the sum difference rule, we can take their derivatives individually. So what's the derivative of 2 to the x? Well, it's 2 to the x times natural log 2 times the 2 to the x plus 1 that was already there. Okay, minus, all right, what's the derivative of 2 to the x plus 1? Again, sum difference rule says you can take the derivatives individually, and so you get 2 to the x times natural log 2, and the derivative of 1, of course, is 0, times 2 to the x minus 1. over 2 to the x plus 1 squared. All right, let's see. I guess I can factor out, look, both of these have a 2 to the x times natural log of 2 in them. Both terms do. So I can factor that out. All right, let's see what happens if I do. I can factor out a 2 to the x times natural log of 2 from both those terms. That leaves us with what? 2 to the x plus 1, and then a plus 2 to the x. Oh, wait. Oh, I about lost a negative sign there. Okay, here, let's do this carefully so that I'd factor out. Oh, what just happened? Oh, come on. Oh, give me a sec. Not sure why I went back to the beginning. There we go. Okay, so let's find my cursor again. All right, so we factor out the 2 to the x natural log of 2. So that leaves us with 2 to the x plus 1. Oh, but then it leaves us with a minus 2 to the x minus 1. So I almost lost my negative sign there originally. So divided by 2 to the x plus 1 squared. Now that gives us what? Okay, if we do a little simplification, of course we have the 2 to the x plus 1 squared on the denominator, but on the numerator we have that 2 to the x natural log of 2. And what do we get in the parentheses? Well, okay, we have 2 to the x minus 2 to the x if we distribute. But then we have 1 minus negative 1. So that's 2. 1 minus negative 1, 1 plus 1 gives us 2. Okay, so let me rearrange the top a little bit. So we're going to have a 2 left over. Interesting. So that's going to be 2, I'll bring it out front, times 2 to the x times natural log of 2. Lots of 2's in there. You know, I suppose if you want, remember, that's 2 to the first power. If that's 2 to the first power, then you can actually rewrite those first two terms as 2 to the x plus 1 power. That would even make it look a little nicer. So 2 to the x plus 1. Because, again, I like this. We have, if we have a times a to the x, well, you have the same base. That's understood first power. So this would equal a to the x plus 1 power. So same kind of thing going on there. Okay? Always want to simplify. Simplify as much. Oh, what did I just do? Just lost something. Always want to simplify as much as possible. Oh, I lost a minus 1 there. Okay. All right. What about C? Okay, C. Oh, interesting. C is composite again. Oh, C and D are both composite. But again, we don't have this thing called the chain rule yet. Coming soon enough. But we can use properties of exponents to rewrite both functions in C and D and then apply the properties of derivatives that we know so far. So let's rewrite h of x. H of x can be rewritten as log base 3 of x to the 1/2 power. Okay? Which then what? We could say this is what? 1/2 times log base 3 of x, right? We can bring that exponent out front. Okay? So, now we can, oh, not equals. We're not going to do that just yet. What we want to do now, since now, no calculus yet. That's just algebra. Now let's take the derivative, because now we have a constant multiple times a non-base e logarithm, which we can work with, because we have the constant multiple rule, and we know how to differentiate a non-base e logarithm. Now it's no longer composite, in other words. So h prime equals, okay, if you take the derivative of the entire thing, you have 1/2 log base 3 of x, but the constant multiple rule says you can bring that 1/2 out of the derivative. And now we just have the derivative of log base 3x, which gives us 1/2. And then, of course, the rule on the top of the page says the derivative of log base 3 is 1 over x times natural log of 3. So I guess if we want to write this in more condensed form, we would say, 1/2 times that fraction is 1 over 2x natural log of 3. Cool. What about d? What about the function of part d? Again, we're going to use the properties of logarithms to rewrite this so that it's not composite, because we don't know how to work with composite functions in general yet. But we can use that product rule again. We could say that f of x is log 100 plus log of x. Right? That's the product rule that we used recently. Okay, so now I can differentiate and say f prime is the derivative of these individually, log base 100 plus the derivative of log x. And remember, what is log 100? Oh, actually, you should know that off the top of your head. What is it? What is the base if there's no base specified, at least in math class? In math class, if there's no base of your logarithm specified, it's base 10. So this is asking for 10 raised to what power gives you 100? It's 2. That's 2 in disguise. So what's the derivative of 2? It's 0. It's a constant, 0. Plus, and then what's the derivative here? Well, it's 1 over x times natural log of the base. But again, the base is 10, so natural log of 10. So we get 1 over x times natural log 10. Cool. So there's some examples of derivatives that involve non-base E, non-natural logarithms, and non-base E, non-natural exponentials. If you have any questions, always feel free to reach out. More than happy to help. I'll see you in the next video.